Hello students, we were discussing about the CDMA environment and multi-user scenario in a CDMA environment when the practical system is deployed. Today, we will try to understand the in a multi-user scenario, how optimum detection is possible in the receiver. This discussion is divided into two parts. Part 1 will be discussed in this module, and in the next module we will discuss the remaining portion of the multi-user detection section, optimum multi-user detection, and followed by in the third module we will discuss about the error probability calculations for this optimum multi-user detectors. So, let us start. The multi-user detection, the problem specifies the fact that we are having in a wireless situation, say k users operating simultaneously, trying to access the channel simultaneously and sending the data to a receiver, and it is not like that all the k users are targeting to a typical receiver. It is something like that each of these users are targeting their independent intended receiver, but as all the receivers are turned on in a wireless environment and going by the fact that the receiver antennas are omnidirectional as well as the transmitting antennas are. So, in the receiver you are receiving the signals from all the direction and from all the users. And so, in a CDMA, so the channel that you are visualizing in such an environment is a k user channel model, where k is the number of the users are currently operating or accessing the channel, and the signal in a receiver received in a receiver front end, it can be viewed as the sum of the antipodal modulated synchronous signature waveforms which are embedded in relative wide Gaussian noise. So, the signal received at the front end of the receiver, if I denote it as yt, it will be a combination of the signals coming out from the different number of the users. If I have capital K number of the total users, so I will get the sum of all those transmitted signals, and it is embedded, embedded with a relative wide Gaussian noise section. Remember this T of it is a continuous domain signal, received signal, and this T can vary between 0 to capital T, and this capital T is inverse of the transmitting data rate. Inside this equation, the SKT denotes the deterministic signature waveform, which is basically the spreading code that you have given to independent users, which are from user to user it is varying. It is a typical signature waveform, that is why we are calling, and assigned to the kth user definitely. So, that is why the k is specifying. Bk is the transmitted bit, which can be either +1 or -1 for our kind of consideration. So, it is an antipodal modulation going on. Either you are transmitting +1 or you are transmitting -1, only the two level signaling going on, and AK is the received amplitude of the kth user in the receiver terminal. And we understand that ND is a Gaussian noise which is having a power spectral density considered here to be 1, and a noise power in a frequency band which is having a bandwidth of capital B is given by 2 sigma square B, and the sigma square is the variance of the noise, and remember that means our signal transmitted by each and every user is bounded over the bandwidth of capital B. So, that is our assumption. So, these are all the assumptions associated with this equation 1.1. So, now you have received this continuous domain signal at the front end of this receiver, and in a CDMA receiver, basically in a multi-user detector, the front ends of objective of the front end of the receiver is basically to obtain the discrete time information from this continuous time received signal at the received by the antenna. And this can be easily done. We have seen all the structures, the correlator based structure, match filter architectures, which help us actually to change the continuous domain signal, receive signal, to get the sampled vector, or to make it actually change it in the vector form. We can get the sampled vector, sampled output at the output of the match filters. And this can be actually, we can go ahead with when we are detecting it via the match filter or the correlator architecture. We simply multiply this continuous domain incoming signal with the corresponding signature waveforms of the different users, and then we sample it with a proper rate, and hence we get all the orthonormal vectors at the output of the match filters, the correlator sampler architecture or the match filter. This is a very known architecture that we have discussed several times when we have talked about the receiver architecture of a spectrum communication system, as well as we have discussed about the CDMA receivers, code division multiple access receivers, and this is repeated once again. So, YT is the incoming signal of our interest, and we have a bank of the correlators or the bank of the match filters. Filters are matched, the response of the filters are matched with the user 1 to your user k, and hence it is if it is a synchronous channel, that means all the user signals are heavily synchronized, and with zero synchronization error, you are expected that you are getting, actually it is expected that you are getting all the incoming signals aligned to each other, and hence as they are using the same bandwidth and most probably the same data rate also, then their sampling rate will be also unique, and the output of this bank of the match filters, you are going to get the vectors from y1 to yk. So that's all the way actually the initial, this is a set, this y1 to yk is a point of our interest based on which the detector starts working. And so this is a discrete time k dimensional vector presentation by means of the match filters, which is a very fast work that a receiver does, SADMA receiver does. If I express the same theory in the mathematical term, so we will see that inside each and every match filter we are integrating the incoming signal, multiplying basically with its own signature waveform matched to that typical users, and then integrating it over the duration of our interest, and like that everywhere the whole bank is working, and at the end we are getting yk, we are getting a bank of the discrete random variables, so y1 to yk, and this yk, any one of this sampled output of the match filter, if you try to see it with basically now this yk can be now rewritten as ak into bk plus this summed up terms plus the nk. This is for the kth output of the kth match filter matched to the kth user. So, what basically these three terms are saying is, you are getting the intended signal back, you are having actually this is the bk is the intended transmitted symbol, and which is associated with a typical amplitude which may not be exactly equal with which you transmitted, it may be some distorted form of it, and then you are getting interfering parts where actually it is the signal you are receiving, same signals aj and bj you are receiving, where the j can never be equal to the kth users, because the kth user term is out, it is considered in the first term, and here for all the j other remaining users you will get another term associated with them, which is given by the rho jk. This rho jk is basically a normalized cross correlation between two waveforms, means sj and sk. So, this is taking care of all the related based on actually the cross correlation between the two signature waveforms, equivalently two different code set, utilized given actually to other users. This parameter will be contributing or putting the amount of the interference on this received internet received signal. Nk as usual is a random variable, Gaussian random variable which encounters the noise component, and which is a contribution from the noise component associated with the process, and it is having a 0 mean and the variance sigma square we understand. Remember, this Nk can be expressed like this, where Nt with getting multiplied with independent signature waveforms and integrated over 0 to t. And so, this expression of this 1.2 in the vector form in the easiest way we can also write down as capital R capital A B plus n, where this each and every body associated with this expression, they can be signified like this. Capital R is the normalized cross correlation matrix. Capital this y vector, this bold y, it is actually the combination of this vectors y1 to yk. Correspondingly, B will be a combination of B1 to Bk. Capital A is the diagonal matrix representing from A1 to Ak. So, associated to each and every transmitted vector, transmitted symbol, you are having amplitude, corresponding amplitude you have received amplitude variable, and that is varying from A1 to Ak with it. The values are actually random, and these values are also not deterministic, and they are a diagonal matrix associated with this capital A. N is the 0 mean Gaussian random vector with it is also having some covariance matrix, because you see the expression of the Nk is observed actually by multiplying the spreading waveform SKT associated with it. So, as a noise spectrum, we understand in the spectrum communication that the noise spectrum will be spread in the receiver once multiplied with the signature waveform, and if we take the, hence it will be also associated with the covariance cross also with the cross correlation matrix, and that is why the covariance matrix of this noise, which is given by basically the mean of this n into n transpose, it will have actually the relation with this cross correlation matrix capital R. This cross correlation matrix is a contribution of this signature part, signature waveform, and multiplied with the variance of the noise. So, what we are ending up with is once actually at the end of the output series of the match filters are employed, at the output of the match filters, if we see combinedly, we will be able to see matrix representation of the, which is the combination of the transmitted signal vectors, cross correlation matrix, the noise matrix, the transmitted matrix, and the received amplitude corresponding to that transmitted signal matrix, and you are ending up with a combination of all these three given by equation 1.3. Now, the question is the conventional single user match filter receiver architecture, does it require any knowledge of the other users present in the network? Its answer is no, because if it is a single user match filter case, then he only needs to know his own signature waveform, and he also needs to know the timing of that user. That is all for his own demodulation. In a multi-user CDMA receiver, actually this model is extended to the bank of the match filters. So, you need the bank of the output of the bank of the match filters. So, and which are modeled as some random variables. Remember, in a CDMA situation where the multiple users are on, you also need to know the signature waveforms of all the users for optimum demodulation and detection, and then you also need the timing information of all the users. We will show that on the top of it you also need to either know a priori or to estimate the values of the amplitudes for all the users you are receiving corresponding to all the users, the signal you are receiving corresponding to all the users. So, the amplitude of each and every symbol transmitted by all the users, and also the variance, noise variance is an important factor that you will be you must be knowing, or you must be knowing, or you must be estimating in some way, so that your detector performance is improved. And remember, actually in the CDMA receiver for the long time it was widely believed that the decision of this conventional single user match filter, if not optimal, that it will be also optimal for the channels where the large number of the equal power users are present. So, if they are equal power users and the number is very large, we can approximate the consideration of the channel with a Gaussian channel, and then finally the single user match filter performance will be actually sufficient to be close to the optimal performance. And this conclusion of this near optimality of the single user match filter came from the fact that people were believing that the observables that is used to demodulate, suppose the user 1 must be sufficient, and they restricted actually the demodulation process for a typical user to be associated with the his own match filter output only. So, though actually he was receiving y1 to yk, and the detection process of the match filter output for a specific user, actually for that only the corresponding match filter output was getting used. There was the concept of actually utilizing the all the vectors available, and but that is why actually this optimality was assumed, and this optimality, but in practice this optimality does not hold good. I mean, match filter based, single user match filter based optimal solution that people were believing, it is not really true. This is due to the fact that though y1 to yk, the match filter outputs, they are sufficient for statistics for the whole data bank b1 to bk that was transmitted, but remember that yk only the one-to-one correspondence, I mean yk alone is not sufficient statistics for the bk. As a whole, y1 to yk is sufficient statistics for the data bank of b1 to bk, that is true, but the vice versa is not true, saying that the yk will be sufficient statistics for bk. Now, we will slowly enter into to design the optimal detector or understand the optimal detector performance and its architecture. We will take an example of two user synchronous channel. So, in the channel we are having only two users, the transmission is synchronous. So, they are time synchronized, I should say, and so the output of the channel equivalently the input of the receiver should be given like this. So, I have extended the initial expression I showed at the beginning. Now, I am breaking it up, and you are basically receiving A1 B1 S1 T plus A2 B2 S2 T plus sigma N T. So, the signal corresponding to the user number 1 plus the signal corresponding to the user number 2 added with the AWGN noise, that is all it you are receiving. So, the minimal error probability, the decision that corresponds to the minimum error probability for the user 1 will be obtained by selecting the value of this B1 where it belongs to either -1 or +1, such that this a posteriori probability given by this expression, where you are given the what is the probability of the B1 given that this yt is received and the t is varying between 0 to capital T is all about the a posteriori probability. So, the value of the V1 that maximizes this probability will be the minimum probability of error decision. So, if this a posteriori probability is maximized, the value of B1 for which this probability will be maximized, that will also minimize the error of received error in the decision process. So, that is a relation. Equivalently for the user number 2 also, the probability a posteriori probability given for the B2 given the signal received will be the value, the B2 value which can actually maximize that probability will be also confirming that the error probability will be minimum. So, in the similar way for the B2 also we can devise the detection process. But remember, this is actually individually you are trying to, this is the process which we call actual minimum error probability approach. But there is another approach where we do not look into the B1 only or B2 only, rather we prefer to go ahead with a joint a posteriori probability. It is not an individual a posteriori probability given by 1.4, rather we selects a pair of the B1 and B2 in such a way that the joint a posteriori probability, means probability of B1 comma B2 given the signal received over the duration of 0 to capital T, this probability is maximized. So, now see there are two approaches. One is actually individually you try to maximize the a posteriori probability, choose a typical value of the received signal to choose a value of the B1 such that this probability a posteriori probability is maximized, or you try to maximize the joint a posteriori probability by proper selection of the joint pair of the incoming pair of the data. So, these are the two approaches. We will discuss about the pros and cons of the both approaches, and remember we say one guy is as a jointly optimum process, another one we will refer as individually optimum. So, the first one is the path for individual optimality, and this is the path for the joint optimality for the decision of a optimum detector. So, we will start with solving the first case, which is the jointly optimal decisions, and we understand that we have a pair of the signals in our hand B1 and B2, and both are equiprobable. So, we can have 4 different hypotheses mentioned here as x1 to x4, and the hypotheses are such that the first one x1 is talking about the a1 s1 plus a2 s2. It means actually both are having the positive signs, and here this is a plus minus situation, this is a minus plus situation or the minus minus situation. So, for each and every one actually every situation we have assigned one hypothesis, and the likelihood function that selects this pair B1 B2 that maximizes. So, likelihood function should select this pair of, I should say this should select a pair of B1 and B2 such that those pairs should maximize this equation 1.6. So, basically this maximization process you see actually on the right hand side, it is the exponential of this error, it is a noise section basically. Yt was your received signal and this is two synchronous channel. So, it is basically the signal that you received A1 B1 S1 T and A2 B2 S2 T, the addition of these two you have received. So, when I am subtracting from the received signal this section, I mean signal portion of it from the received signal, you are left with the noise. So, fundamentally you are trying to maximize this function, that means you are trying to minimize this side, and the pair B1 B2, the likelihood function that selects this pair, it tries to maximize, it selects such a pair that maximizes this equation 1.6. And as we understand this B1 B2, they are equiprobable, they are independent. The joint optimum decisions are basically the maximum likelihood decision equivalently. It is chosen such a way that this combined effect of this A1 B1 estimated with estimated value of this B1 and B2, that A1 B1 estimate is 1 plus A2 B2 estimate and is 2, they will be very close with the transmitted signal equivalently with the received signal with a minimum square error sense, minimum square sense. I mean, if my estimation should be such that with the estimated value this expression, whatever the value this expression will give, and whatever actually I have received, they both of them, the error between this between these two signals, if I try to find out the mean square error fundamentally between those two signals, it should be very minimal. So, in that sense actually there is with the estimated values of B1 B2, this expression value and whatever you have received, both of them should be close to each other. So, that is why if that happens basically, then we see that we call that this B1 and B2, the estimated values, they are the likelihood decisions, maximum likelihood decisions. So, thus we choose the hypothesis that corresponds to this noise realization with the minimum energy, and this minimum distance decision region, which we have shown in this next slide. This is the minimum regions that we have shown here. Basically, actually in the 2D space, it is such that this y1 tilde and y2 tilde, which are the projections of the received waveform on the orthonormal signals, that form a basis. They will form the basis for the space spanned for the signature waveforms S1 and S2. So, these decision regions are we have shown for this signals, transmitted signals, signature waveforms S1 and S2 in that figure. As far as we understand that we are trying to decide the 4 signals, and combination will be such that A1 B1 S1 plus A2 B2 S2 is the closest to the received signal. We can disregard all the infinite number of the directions over which actually the contribution to those contribution of those dimensions on the decision of the B1 and B2 are almost nil. I mean B1 B2 does not have any information to those directions. So, in the 2D space we have not included all those infinite number of the dimensions, and only the related dimensions are included in that figure. And remember, it always selects the closest hypothesis. That is the idea about in the received observation. So, the jointly optimum detector, they never suffer from the anomaly, they does not suffer from any anomalous behavior of the single user match filter based architecture. So, there is a balance always actually if you are taking the decision based on the single user match filter output, single output, observation output. So, the anomaly in the behavior that we will suffer with here because of the decision made jointly over the 2 different users. So, there is a balance incorporated in the whole decision process, and that is why actually the anomalous behavior can be avoided completely. But remember one thing, that this individually optimum multi-user detector and the jointly optimum multi-user detector, if I try to compare between these two, first one, the individually optimum multi-user detector, it achieves a minimum error probability error for each user, and jointly optimum multi-user detector, which has a very lower complexity, and unless the SNR is really very low, his error probability achieved by this maximum likelihood solution, it is extremely close to the very minimum one. So, question is actually if I can attain the minimal error for each and every user for by the fast approach individually optimum multi-user detection, why I should go ahead with the jointly optimum case. If the question comes like this, then the answer is this jointly optimum one multi-user detector, they are very low complex compared to this individual optimum multi-user, and if the SNR is not only very much low, they can actually give a low error probability error also, low error probability also, because maximum likelihood estimation is involved, and it can be very close to the minimum very close to the minimum error probability promised. And so, we will see actually at one point the fundamentally the individual optimum multi-user and as well as the joint optimum detection process, both the way they will try to converge at a point. So, this figure we have already discussed about, and this is these are the decision region shown for this kind of the values of the A1, A2 and rho. Rho is we understand that is a cross correlation factor, and this is actually the another situation where the relation between A1 and A2 is something like this, and the rho is also having some different values. So, let us see how do we implement this optimum decision rule that selects the closest hypothesis to the observations. So, we understand that this is the likelihood function we have seen earlier in some few slides back. If this is the maximum likelihood function, the likelihood function, sorry, it is not the maximum one, it is the likelihood function based on which the decision is obtained on the B1 and B2. I can actually write this expression also like 1.7, where the factor this big omega 2 can be expressed like this, and the matched filter output, we understand that it is denoted by this expression y k equal to 0 to t y t s k t, and rho represents actually the cross correlation of two signature waveforms. So, these are the identities of these are the identities used or the symbols used inside this expression 1.7, and if these are the expressions, if this is the explanation of all the symbols, with that remember this right side equation of this 1.7, we can disregard the factors that do not depend on the B1 and B2. So, basically our target from this expression is to estimate B1 and B2. So, the factors which are not dependent on B1 and B2, those factors can be disregarded from the expression itself, and we can thus come down, and then the maximum jointly likelihood decision, which is the jointly optimum decision also, are those that maximizes basically the function this big omega 2. So, what are those? It can be checked easily that this optimum decision are such that if the minimum of A1 mod y1 and A1 mod y2, whichever is the minimum, that should be greater than equal to of this A1 A2 into mod rho. If this satisfies, then only we can get the optimum decision, and for such optimum decisions the values of the B1, estimated value of the B1 and B2 will be given by the sign of this y1 and y2 correspondingly. Otherwise, if the situation is not valid, then you will get the decisions of B1 and B2, the estimates of B1 and B2 will be governed by these two expressions. So, think a situation actually, if whatever the figure we have shown here, referring to this figure number 2, where actually my rho value is greater than 0, the condition that this minimum value of this A1 mod y1 and A1 mod y2 greater than equal to this, it checks whether or not the observation are closest to either +1 or -1 So, basically it is trying to see whether you are in this zone or you are close to this zone. Okay. So, and then in which case the decisions of the conventional detectors will be the optimal. If the observation does not fall in this region, regions of either this or -+1 or -1 So, then actually basically you are checking whether the observation are close to +1 -1 or -1 +1, and this is basically equivalent to testing whether A1 y1 is greater than equal to A2 y2 or not, because rho is greater than 0. So, these are the two ways the detector is basically working upon, and we can actually also justify the same results on the other fact, where the rho is having some different values, or the relation of the A1 and A2 is also having some different values. Now, but this is universally true, and for the optimal detector part, that this is a fundamental two part based on this minimal check points of the optimal decisions can be obtained either this or this. And fundamentally in the graphical way also we can understand that finding out that whether this is greater than this, I mean this guy greater than this, is finding it means basically you are trying to find whether the observations are close to these two regions or not. Otherwise, actually if they does not fall into this region, then basically you are trying to find out which one is greater than which one. So, this is the way the optimal detectors, the fundamentals of the optimal detector it is. In the next module, we will see in some details considering the k user situations how the detector performs.